really pleased to introduce Laure Zanna, the large number of people in this room actually know pretty well. She has a very interesting career because I think she explored the most countries I know in terms of faculty positions. She started with a PhD here at Harvard with Eric Zimmerman. Actually, she started, I guess, with a master in Weizmann, then moved with Elia here to Harvard and did a PhD. And already at the time, that's when I first met her. She was working on data simulation, how to use data and models in a pretty creative way compared to what most of the group at MIT was doing. And I guess starting from there, she started pursuing a career that is more and more trying to take advantage of the observational information we have about the climate system. And she did that first as a faculty at Oxford and now as a faculty at New York University, where she's leading these two major projects. One is the climate process team that works mostly on machine learning-based approaches to represent the effect of large-scale ocean turbulence in climate models. And then she's also leading a second project with Schmidt, funded by Schmidt Futures, that is really looking, again, machine learning, but to parameterize all subgrid scale processes in couple models. She's also involved in another major science and technology center in Leeds, in collaboration with Columbia and I guess M². And they are trying to expand it, again, machine learning, or in general, how do you take advantage of data to improve the approach to climate models. So she's really at the cutting edge of trying to explore how machine learning and artificial intelligence in general can be potentially used to improve our understanding of the climate system and also how we project it. Thank you for coming, and I'm sure it will be a great seminar.
Great, thanks, Raf. Thanks everybody for joining. Definitely very excited to be here. Never been in this building, but always fun to be back at MIT. So as Raf mentioned, what I want to talk about is very much this idea of how can we improve global climate models with AI or machine learning. I think nowadays we can use both of them, kind of interchangeably. Very much kind of using data, wherever that data is coming from, that is truthful, to help model development and basically improve our climate simulations. But along the way, the hope is we also learn something, right, about the process and the physics that we do after. I was trained in a bit of an old-fashioned, if one wants to say, without machine learning and without AI, but really trying to understand the physics of different processes. So we're really trying to merge those kind of two concepts together. Is there something from the data that we can learn? And when we learn that, can we actually improve global climate models? So I'm here talking, but again, Raf mentioned several projects that I'm part of. I'm going to mostly talk about some work with the M²LINE team, so it's funded by Schmidt Futures. So here are a lot of the people involved in the project. It's oceanographers, atmospheric dynamicists, sea ice experts, climate model developers, machine learning experts, really everybody trying to combine those different approaches together and really pushing forward the improvement of climate model for different components, sea ice, ocean, atmosphere, altogether, many institutions, actually including MIT with the atmospheric group. So again, I'm the one talking, but all the great work is done by these people. So I'm just privileged enough to just talk about it. So gonna give you a little bit of kind of three bullet points in this talk, right? So first one is I'm gonna try to motivate a little bit what's going on. So, climate models are the primary tool for understanding and predicting climate. So I'm going to motivate that a little bit. I know many of you are familiar with it, but not everybody. So just kind of tell you a little bit the challenges we're facing with climate models. The second one is going to be the core of what I'm going after here is, can we accelerate model development and model improvements with machine learning? And the idea will be to kind of reimagine or reinvent the way we represent a lot of the processes that are not captured by large-scale coupled climate models. And so that's really going to be the focus of what we go after. And of course, I'm going to show you things that work. I'm also going to show you things that don't work, and trying to think a little bit about, where should we go from here, because not everything is solved. Not everything is done and dusted. I think there's a lot of things to think about, and hopefully, there are a lot of students and postdocs in the room. I mean, that's going to be probably, some things you might be interested in doing in your career, because I think the field is advancing, but we would like it to advance faster. And so that means bring people from multiple, backgrounds and multiple, ideas to push this forward. Okay, so I'm an oceanographer. So basically, most of the motivation of my work come from understanding how the ocean takes up heat and carbon and all those other things. and how it influenced the large-scale ocean circulation. So here's a plot from the, the IPCC. So here, what's plotted is global ocean heat content as a function of time. What's in greenish or cyan are observations or reconstruction. And so what you can see is that the ocean has been warming, right, at a given rate. Now the black curve is basically climate models trying to reproduce that warming. Okay, so try to reproduce the past. It does a decent job overall, right? The shading is the uncertainty, meaning different models have slightly different rates. But over the observational period, it does a decent-ish job with some uncertainty. Now, if we go into the future, well, the future will depend very much on how much greenhouse gases we put in the atmosphere, right? So we're going to warm the atmosphere. A lot of that heat is going to end up being in the ocean. Now, how much warming will the ocean experience? Then different model will actually give you a slightly different answer. So if you take a given color in those simulations, so now we're going into the future, up to 2100, we made an assumption of how much emissions we'll put into the atmosphere. And then again, the shading is going to be basically every single model scenario. And so every single model realization for a given scenario. So the shading tells you basically that models that receive exactly the same amount of emission will actually warm at a different rate. So different climate model will give you different answer for how much the ocean will be warming for a given amount of basically CO2 emission and other greenhouse gases.
The absolute heat content of the models historically close to each other.
Yes, so I mean, of course, ocean heat content is always relative to something. So if we're looking at that, so if you divide per unit global warming, the spread is actually twice. So we have between 0.5 watt per meter square per degree Kelvin to 1.2. So it's a pretty large spread for a given scenario. It's actually pretty substantial. So models will take up heat at different rates in the ocean. Now, why? Technically, they solve the same equation, right? And so that's kind of the challenge here. So I was in the physics department for many years, and my colleagues used to tell me, what's your problem? You have equations. Can't you just solve them? Right, and that's a fair statement. So if we look at the governing equation for the ocean, they look something like this, right? We have momentum, so basically our F equal ma, our Newton's law. For parcels of fluids, we have conservation of mass, heat, salt, and an equation of state that basically kind of combine density to temperature, salinity, and pressure. Now, those equations actually represent all the scales of motion in the ocean. So really from the large scale, thousands of kilometers driven by wind and buoyancy that will kind of drive the currents, all the way down to meters, right? Or basically the dissipation scale that is very turbulent. And all along the way, all those scales interact with one another. So those instabilities, those mesoscale instabilities at, basically kind of 100 kilometers in scale are derived from the instability of the large scale, but they also re-inject energy and momentum into the flow so they can accelerate the currents and so on and so forth. You can make this kind of same connection across all scales. They really interact over a full spectrum. So those equations are wonderful. They can really describe all motions that we have in the ocean, but obviously we can't solve them, right? I mean, can get a millennial prize if you can find unique solutions for the Navier-Stokes. And so again, because of the richness of the spectrum that we have to deal with, what we do is we usually discretize them in space and time. The discretization and the numerics obviously will mean that we're going to introduce some errors, but most importantly is as we discretize those equations, the compute cost goes up, right? So the finer the grid box that you have, then the computational cost will go up with it. So if we were to assume, just for the sake of argument, that I wanted to resolve all the scale all the way down to basically a meter scale, and I wanted to solve the ocean equations for 1 meter cube, right? So if I discretize my equation, want to take a parcel of fluid 1 meter by 1 meter by 1 meter, you'll end up with 10 to the 28 equations to solve. So I know we have new models at MIT that are coming up faster than ever, but it's still going to take us a while, right? If I want to do climate simulations with large ensembles running for hundreds of years, if I really want to resolve all the scale. So we're still going to get stuck in this world of we don't resolve all the scales. We're going to truncate. Usually we truncate around those scales about 10 to 25 kilometers. And that means a lot of the physics is going to be missing from our simulations. And so that's just a nice animation to just show you a little bit kind of the difference cross resolution. So this is a fully coupled climate model. So it has all the bells and whistles, basically solved for the ocean equation, the atmosphere, the sea ice, the land, and so on. And what we see here is the Antarctic Peninsula, and we're looking at sea surface temperature. So it's a simulation of sea surface temperature in those simulations. Same model, but run at 3 different resolutions. This is 100 kilometer over here on the left, in the middle, 25 kilometer, and on the right is about a 10 kilometers, so 1/10 of a degree. So obviously what you can see is something pretty obvious, right? It looks like peanut butter on the left, it's pretty viscous. The grid box size is relatively coarse. A lot of the turbulence is missing. As you increase resolution, then of course you can see a lot nice filaments, some stuff kind of going on all the way around the peninsula, some kind of, sharp jets, on the flanks of, the shelf of the Antarctic Peninsula. So we can resolve more turbulence, we can resolve more physics as we increase resolution. But of course, it's just that the movie is just pretty, right? It actually also changed the rate of ocean heat uptake because it changes actually the stratification in those places. So more physics also improve a lot of the large scale, physics that we care about very much. Now, again, our typical global coupled climate models are not run at this resolution of 1/10 of a degree, right? So the current models that we have are about this kind of 25-ish kilometers for the majority of them. Some are still run at 100 kilometers. And I should mention 100 kilometers, when I say that, I'm talking about horizontal resolution. I'm not talking about anything in a vertical for now, and that will be for the rest of the talk. So this is our challenge, right? We end up with models that are run at those typical resolution, where a lot of the physics is actually missing. And one key element of that physics that is only partially resolved are those kind of mesoscale eddies, which have about, again, 10 to 100 kilometers in scale, are important for steering and mixing, tracers in the ocean and for setting up stratification, also meaning they actually set up the rate of ocean heat uptake. And so again, we have some theory that actually shows that. I don't know how it works, but you should feel free to interrupt that, by the way. I kind of enjoy the questions as we go along. So since we can't resolve all the scales, again, because we're limited with compute power, lots of physics is missing. Traditionally, for decades, the way we've been doing that is trying to represent the missing physics with some approximations, okay? So basically, if you look at atmospheric models, clouds, turbulence, radiation, all of that is actually happening at a scale that is much smaller than the grid box size of the climate model, so they need to be parametrized. And for the ocean, it's pretty much the same. Most mixing processes in the ocean also need to be parametrized. And so the way people have done that typically is to actually come up with a representation of those kind of, subgrid forcing in terms of a functional form that depends on the resolved scales that you have. So try to come up with a relationship that will depend on the large scale that you can resolve in your climate model that will impact, again, your large scale climate, just mimicking the effect of the process that you're missing. So you can think about mixing, for example, right? It's going to be too small to be resolved by the climate model. The goal is trying to come up with a function, a mathematical function that will mimic mixing. And so you can think about the Laplacian of your tracer, and you multiply it by some coefficient that will just basically really try to represent the mixing that you have in the system. It's pretty ad hoc, right? You try to represent some physics with a simple function, and you put it on the right-hand side of your model, only depend on the resolved scale, and you hope that it does a decent job, right? But again, it's good, and it helped models for a very, very long time, but this is one of the reasons all the model gives us a spread. That's why a lot of the model give us different answers, because they have those kind of, uncertainty associated with the missing physics that we have approximated in a way that is, again, not necessarily super rigorous, or is missing a lot of data in there that is not well informed, and so on and so forth. So those parameterization actually are one of the main sources of uncertainty in climate simulations and in projections. So the question is, can we do better than just coming up with some relatively simple approximation for those missing physics? And so the idea that we had was, can we try to leverage some basically advances in machine learning and AI by using some simulations? So I'm not going to talk about observations that much, only at the end. Can we use high resolution simulation? Because we have some of them, right? It's not like they're non-existent. We have quite a few of them. We just can't run them at the scale that we would want for climate projections. But can we use that data that will be, high fidelity data to extract information about those missing physical processes and learn relationship from the data for all the unresolved physics that we don't have. So that's kind of the game, right? Rather than using ad hoc approximation, replacing them directly by functional form that we learn from data with machine learning. So actually started a long time ago for the atmosphere. It started in the late 90s, where people use neural network to try to actually learn, things like radiation and other atmospheric processes. But there were a couple of papers and then it completely kind of, died out. And nothing happened until, again, the late, I guess, 2010s or something like this, where again, kind of advances in AI show that algorithms were now faster and that you could train them, more easily with new advances, and a lot of things started picking up. And so again, people here at MIT, like Paul Gorman, have actually made a lot of advances in trying to parameterize convection in the atmosphere for that. So we've been working a lot on the ocean side. Again, my background is oceanography. So we've very much focused on many of those ideas of trying to extract, new parameterization for ocean physics from data. So this is kind of, that's going to be a little bit of our kind of a game here, is we're going to use some simulations and we're going to try to extract a parameterization for ocean turbulence directly from high fidelity simulation and trying to learn that relationship between, again, the missing physics that we have in coarse resolution simulation based on whatever the climate model can resolve. So what I'm going to do is I'm going to spend about, a large chunk of the talk just giving you some illustrations with very simple models, just to give you a little bit of almost the philosophy of our approach, which is trying to actually come at it in a more principled way than just trying everything out and telling you a few things. And then at the end, I'll show you a few results actually in global climate models, which are ocean plus sea ice coupled again, and give you with some ideas of where we are and where things might be going. Okay, so we have 4 points that we always try to approach with those ideas of using, AI for machine learning. One is, I want to learn something that is physical, right? I don't want to learn just some kind of random function that is how to interpret, and that might not be super faithful if I'm trying to actually understand the climate system or make projections. So our number one goal is trying to really learn something from the data. That's not always the case, I should make that very clear. But this is one of the goals that we go after. So trying to come up with models that are simple enough where we can learn something about the physics and the scale interaction in the ocean. Second thing, it has to be robust, right? I mean, in a way that if I take a slightly different data set, I should end up with the same answer if I'm trying to learn the same physics. There is no reason for it to be completely different. And so it should have some physics embedded in it. And so this is kind of this idea that if I learn physics with data that I sample in a given model, and suddenly I change the rotation rate, well, technically it's the same physics, so it should still work out. So this is this principle of generalization. F equal ma works on Earth and it works on different planets as well, right? So it's the same physics. So that's very important. Third one is, well, we're in a game of learning, approximations. So we just need to know, we need some uncertainty quantification associated with it, because no matter what I'm going to learn, I'm still trying to learn an approximation of missing physics to large scale. So this is impossible to have something that is purely deterministic and has no error in it. However, we want to quantify that. So that's the third point. Fourth one is, again, I'm learning an approximation for a coarse resolution climate model. I need to go and plug it back in the coarse resolution model after I learned it. And so that's where kind of, scientific computing still exists, meaning quite often things blow up, right? So you end up with numerical instabilities or some nonlinear feedback between your coarse resolution equation and whatever, new force you added on the right-hand side. So those 4 points here are things that we have to take care of in different ways. And I'm going to just, again, illustrate things that work and things that don't work as well, just to give you a bit of an idea. Okay, so I'm going to start with a very simple model. So it's kind of the bread and butter of, physical oceanography in a way, or geophysical fluid dynamic. It's called a quasi-geographic model. It can resolve those kind of mesoscale eddies that are, deriving their energy from large-scale instability. And they can re-inject energy into the large-scale flow. So they have an inverse energy cascade. So that's why they're pretty important as well in driving the large-scale currents. So just again, schematically, what we're looking at is a snapshot of what we call potential vorticity. So again, nice combination of conservation of momentum and thermodynamic properties in this model. So we're looking at a snapshot of this potential vorticity in a high resolution model, and then in a coarse resolution model. So it's the same equations, they just run at different resolution. So of course it's a snapshot, you just need to take my word for it. I'll show you a couple of other quantities, but you have less energy at low resolution because those eddies are not well resolved. So obviously you truncated part of the energy cascade. The flow is a little bit more boring, but nonetheless, you do have some eddies there, but less energy that you would want. This is a two-layer model, yeah. Yeah, correct. So prescribed background stratification, and then basically letting it, evolve, but basically continuously forced. Yeah. Okay, so what we've done is we try to learn two parameterization from data and compare it to what I would say is the best parameterization, best physics parameterization that is out there. So the way we do that is we're going to run the high resolution model. We're going to filter it, coarse grain it, and then learn this relationship that I showed you here, the subgrid parameterization as a function of the bar, which is only the things that are being resolved by the model. And we're going to learn two parameterization. One of them, a full-blown neural network. I have no idea what's going on in there, lots of layers, lots of parameters. We put a physics constraint in it because momentum has to be conserved, globally. But again, I let it do whatever it wants and with a lot of weights. Second thing, we try to discover an equation from data. So there, rather than tell the algorithm to learn a huge number of weights, we ask it to learn a model that is as sparse as possible, or with as few terms as possible. There are two different algorithms that one can use, and I'm happy to talk about them. But here the goal is, I don't need to fit every single little eddy or every single little forcing. All I want is capture the right amount of physics with as few terms as possible. And we compare it with this physics parameterization, which is, Jensen and Held. It's basically negative viscosity. Very simple, re-inject energy at a slightly larger scale above dissipation. Does a pretty good job. It's being used in many models. It's just trying to fight the over dissipation of the flow and mimics the inverse energy cascade. Oh, if it's constrained with energy, it is. So nu constrained with eddy energy is numerically stable. Oh, yeah, there is always dissipation. Yeah, sorry. In all the simulation we have, there's this D over here. Every single simulation has some dissipation in it. Yeah. Sorry, I always make the assumptions that they are there. Yes, nothing can be run without it. Okay, so in the snapshot world, you'll see almost no difference. This is a negative viscosity. Again, there's just kind of a simple theory that people came up with, and it works. You get a little bit more eddies. If you use a very complicated convolutional neural network, again, you get more eddies. And if you get this kind of symbolic equation, it has very few terms in it, actually has only one coefficient, also, re-inject energy into the flow. So just let's look at some quantities. So this is kinetic energy as a function of time. So the black line is the high resolution simulation. So it has more kinetic energy, right, as I mentioned, compared to the gray line, which was the coarse resolution model. Now, each one of the other curves is the coarse resolution model with those parameterization. So the physics-based one is the cyan one, does a decent job, it gets to the right level of kinetic energy. If we look at the CNN, so a bazillion number of weights, that's the green one. It also gets to a right amount of energy, but you can see it wants to get there very, very fast, right? So it really wants to get as much energy as possible, as quickly as possible. So again, that comes from the training for the most part, because you give it a lot of data from the later part of the simulation. So that's what it learned to get to as quickly as possible. The equation discovery one gets you a little bit kind of somewhere in between based on the kinetic energy, distribution. If we look at probability distribution functions, what you can see is that actually the neural network is the best one. And that kind of makes sense, right? Because you have so many weights that you can capture the tail of the distribution a lot better than if you have very few terms with the symbolic equation or a very simple physics-based parameterization. Just to give you a little bit of an idea, right? So you have more weights with the neural network. It can do better at certain quantities, but it doesn't win on all metrics. But still pretty good. I just have no idea what it did, but it does well. With the symbolic expression, we were able to actually learn what additional physics we included because it depended on the stretch and the shear, of the different simulation. Now, the test is, if I learn on this data that is kind of isotropic turbulence, I'm still learning scale interaction. So if I were running the simulation with a slightly different rotation rate, I should still learn the same scale interaction. There should be no difference. So now we're not going to relearn those parameterization from data. We're just going to still implement them in the same physics model, but with a slightly different rotation rate. So now when you change the rotation rate, you can actually give emergence to jets, all right? So that's the high resolution. Low resolution has some hints of jets in the background, but they fainted. So now what we want to do is to re-energize those jets. And so you can guess who wins, which parameterization will be best, in your opinion. The physics-based one, the deep learning, or the sparse data-driven equation discovery? Okay, so I see people pointing on the right. Yeah, so 1, 2, or 3? Nobody wants to bet? Okay. All right. Okay, it's a pretty broad range. All right, so it's 3. Yeah. So the physics-based one, as is, almost does nothing. So you need to retune it quite a bit to actually get it to work. It's not working, but you need to retune it quite a bit. The deep learning one just went insane. Basically, what it tries to do is to try to make the turbulence more isotropic, because they actually learned too much of the features from the data that it was trained on. So it really didn't, it learned some scale interaction, but it kind of overlearned it in a way that was very tied to the physics itself. So it destroyed the jets completely and tried to make it more isotropic. And the data-driven equation discovery that has very, very few parameters, can be written as a set of equations, was not retuned, does the best. So you don't need a huge number of degrees of freedom to represent very complicated scale interaction that will actually kind of generalize across much of the physics. And that goes back to kind of physics principle, right? You want a model that is as simple as possible, but not too simple. And so that's kind of the idea. From data, you can learn a lot, but you need to know not overdoing it, right? And making sure that you learn something that is physical. Yeah. Yeah, so here, I mean, again, we forced, right? So we continuously forced.
It's the drag, I guess.
Yeah, so it's forced, bottom drag, high
So
drag.
if you change the drag,
that's a good
does it
question.
still work?
Yeah, so that's a good question. We did some sensitivity with different drags and things like this. In this setup, it works. But when we go to more complicated, setups, we end up with other problems that are worse than PV homogenization in a way. But we can talk about this more. Yeah.
Just a question. So you're trying to reproduce the statistics, right? Not the deterministic evolution, correct?
So yeah, right now we're not looking at individual trajectories. We really trying to kind of represent the climate of the system, if you want. For individual trajectory, I feel we try actually. The autocorrelation is not great when we learn the subgrid forcing for the statistics. So yeah, can talk a little bit about this after. Okay, so the winner was the symbolic, expression with very few parameters that, again, we could understand what the physics was. Now, one thing that comes up a lot when you, learn from data and re-implement it in your model, you know nothing about the model that you're going to implement it. And as we all know, they still get discretized. They have their own, numerics. So you end up with some feedback between the parameterization and, your numerical scheme. So this is something we don't know, by the way. Sometimes it works, sometimes it's stable, sometimes it's unstable. I still have no clue when it works, when it doesn't, but there are a lot of papers out there, trying to come up with methods to think about this. And so I'm not going to review all of them, but a couple of papers have, made the argument that we should learn online rather than offline. Right now, we're learning a tendency purely offline with data that we stored. We learn it, we get the expression, then we go and we plug it into a model. I like this approach because if I learn real physics, then I'm going to be able to implement it in any model that I want, right? I can put it in a model that I'm showing here, put it in Oceanagans or Atlas, right? Any model that I want because I learn real physics. But if I do it online, I'm getting tied to the numerical schemes. But again, the advantage is, well, you learn the evolution of your parameterization as you learn it with the numerical scheme. So you might help with stability. So there are a couple of papers, and there are a few more actually in recent months, that argue we should do machine learning online. We really train with a model that is fully differentiable, so you can back propagate, your loss function and really learn the subgrid forcing as the trajectory is evolving. And you can make sure that you don't blow up, basically. Problem is climate models are not possible to have them being differentiable unless somebody wants to rewrite all of them. But I'm out. And so I want to use them as is, right? And so the question is, can we come up with methods that might actually capture the same idea without having to rewrite the full differentiable code? So one way is, so it's worked by one of our postdoc, Chris Pedersen, is to actually try to kind of, cheat, is to learn a loss function offline. But in addition to learning the subgrid forcing and learn a network for the subgrid forcing with input and output, we have an additional loss that emulates the trajectory with a network. And a neural network is fully differentiable, bunch of weights, right? So you can actually backpropagate it into your loss. So this is a way to mimic the evolution of your numerical schemes and your trajectories with a neural network that becomes fully, differentiable, meaning you can do that completely offline without having to have a fully differentiable model. Now the cons is you better have a very, very good emulator, right? So you need to make sure that the trajectory that you learn are really good and mimic the right time dependence and spatial discretization that you go after. But that's one approach that one can think of to try to kind of capture those kind of feedback between the subgrid forcing and the evolution of your equations by learning fully offline without having to rewrite your model. So we get mixed results with that. Sometimes it works very well. Sometimes, the emulator is not accurate enough. So you kind of need to have multiple passes. So, the number of time steps you use in your loss function might be important. So there's still a lot of trade-off that we're trying to understand. It might depend, of course, on the numerical schemes that you use and the discretization. But I think there's a lot of stuff there that, can be quite exciting to think about as well in being creative about those methods. Okay, I'm going to pause and get a cup of coffee, and if you have questions.
So in general here that you're doing short rollouts.
Short rollouts, yeah. So the more rollout you want to do, obviously, the more recurrent passes you need to do within your network. It gets a little expensive in the training parts. And of course, it's figuring out how many rollouts is good, right? At some point, it's a chaotic system, so your trajectories are going to diverge no matter what. So you don't want to capture too long because it's unphysical, and too short, well, your snapshots are so correlated that you probably learn nothing. So it's finding the sweet spot that is important, which is still unknown. Yeah, good question. Okay, another approach for stability is, stochasticity. And as I mentioned, I also like to have some uncertainty quantification in all my parameterization, because again, they're only approximations. So there've been, some attempts by our groups and others to try to use, again, machine learning with some uncertainty quantification to learn, what's going on, in the parameterization in a non-deterministic way. So it's the same model as before, high res, low res, just a snapshot of potential vorticity. Now, can we account for the uncertainty in the parameterization in the neural network? So one thing we can do is, rather than use a mean square error as our loss function, so that means we only learn, basically one-on-one mapping, can we learn a probability distribution at every point? That means I'm going to need to make an assumption that, say the error is Gaussian, and I can learn the probability at a given point for the resolved flow. So rather than learning a one-on-one mapping, at every point, given the resolved flow, I'm going to learn a Gaussian distribution for the missing forcing. So that means now at every point, I'm going to have some Gaussian distribution, and I can run ensembles and sample from those Gaussian distribution that gives me some kind of measure of uncertainty with my parameterization. So you can do it in a simple way in using negative log likelihood when you optimize, and you will learn a mean and standard deviation at the same time. That's kind of a nice little thing, but you need to make a big assumption that all your points actually have no spatial correlation between them in terms of their error, which is definitely a wrong assumption. But it's a simple one because it's easy to train. Now, of course, as you all probably know, generative AI is everywhere, so you don't need to make those assumptions anymore. You can play with things like GANs or VAEs, where now you don't make, there are some assumptions, we just don't know what they are, but now you can learn the full distribution with your entire mapping in a way that does not enforce Gaussianity, that does not enforce no spatial correlation between your different points. Now, what we found is that, both generative AI methods capture the uncertainty better overall. So they can represent the uncertainty missing from our subgrid parameterization in a way that is more consistent with, with the learn or diagnose subgrid forcing. But also something is that they improve performance not just kind of overall on the statistics, but improve stability of the network. So that's been seen in other parameterization, the stochastic parameterizations are helpful compared to the deterministic one, but there's no theory for why, except that you sample in different parts of the attractor, and it might help, but it's not like there is any theory behind it for why it has to be more stable when it's stochastic. So I think, again, it's another avenue where, ML brings new tools, but still kind of, end up with results that have been seen in other simulation, but that we don't quite have a handle on. But now the idea is, of course, we have more data, so we can explore that in a nicer way. Okay, so that was kind of my, first part in trying to illustrate those kind of concepts, right? We want to aid with physical interpretability, and that's something we could do with discovering equations. And again, sometimes you discover something that is really physical. Sometimes it's not at all, by the way. So because you learn an equation that it has physics in it, sometimes we learn things that it made no sense at all. So always have to be careful, but it can help. We want things that are robust. So I showed you that some methods are more robust than others. We have ways to do uncertainty quantification, and I showed you we might have ways to do numerical stability, but that's still a question mark. Now, all of that was in this super idealized two-layer models. And I told you, oh, I want to solve climate modeling and make improvements and stuff. So is that true, right? So for some things, it actually works, which, we were pretty pleased about this. So our goal was very much trying to follow two paths. One that is very principled and use idealized models to kind of push all the new methods and test them as much as we can, to do a lot of simulation in those idealized setups because I can do it. I can try a lot of methods rather than one at a time. But also we wanted to implement things in global climate models as quickly as possible and not wait 10 years to figure out if it's going to work or no, right? And so that's what we've done. So one example is this kind of equation discovery idea. So we use data from high resolution simulation. We extracted an equation for the effect of ocean eddies onto the large scale flow. So we were able to actually learn something from it. We were able to actually understand, how energy is being transferred across scale, how momentum is being transferred across scale. We're able to implement it in M². So M² is the ocean component of one of the, well, I guess two global climate models. So GFDL, Princeton GFDL, and now NCAR. So it's the full ocean component of that model. So we implemented those parameterization in a hierarchy of simulations, again, with this M² code. So it's the code of a global climate model. So here's some idealized simulation where we have the coarse resolution model over here, high resolution model on the right, and in the middle, it's the coarse resolution with parameterization. So you can see the amount of kinetic energy is increased. Again, this kind of idea of backscatter, the reinjection of energy is actually impacting the large scale flow, so it does what it's supposed to do. And up here, that's where we're very happy, is we implemented in a full global model, so kind of this simulation that you see here. So the full global model, implemented the parameterization, run it over the historical period, and then we compare the model with no parameterization versus observations. So over 30 years, the model, so here we're looking at what we call the bias, so the error between the temperature of the model and observations over a 30-year period. Pretty much every single climate model that you will take will have the Gulf Stream that is too warm and the North Atlantic that is too cold compared to observations, because we don't have enough heat transport from low latitudes to high latitude, in part because we don't resolve those ocean eddies. Now, if you implement the parameterization, that's the effect of our parameterization on the flow. Gulf Stream was too warm, the parameterization actually cools it. Over here was too cold, the parameterization warmed it. So basically what happened is this kind of equation discovery parameterization did what it was supposed to do. Reinjected energy into the flow, accelerated the eddy mean flow interaction, increased the heat transport to high latitude in the North Atlantic, and reduced the model error that has been present in those models for decades. So it's, it's kind of a way, and that's been done in less than 3 years. So it's pretty exciting that now we have this kind of ability of learning something new from data, implemented all the way in climate models and really test their effect. Now what's missing, of course, is right now it's a global simulation, but it's ocean plus sea ice only. There's no atmosphere. So hopefully in a few weeks, we'll be able to show you the improvement in a fully global model with the atmosphere. But it's still pretty exciting that we can do that. And that's not the only one, right? We were trying to push the improvement or the implementation or incorporation of those parameterization in climate model as quickly as possible, again, to see if it worked at all or what breaks. So here's another example. So that's a little more advanced in a way. We learn a stochastic parameterization from, again, this kind of global data I showed you at the top, 1/10 of a degree. So here only from the ocean, we learn a stochastic parameterization. It's a full convolutional neural network, has tons of weights, many layers, awfully computationally expensive because again, you really kind of increase number of degrees of freedom that the model has to interfere with. But we're able to implement it in MAM6 simulation. This is done with Hewlett-Packard, with one of their basically kind of advanced techniques to easily connect the Python model with, I didn't tell you, but climate models are in Fortran. So basically to have this inference between the Fortran and Python model in an easy way. This is just the proof of concept simulation. It's 1 year only, but we can now implement basically fully convolutional network within, basically global climate models. So again, I can't tell you if it improves anything because it's 1 year only simulation, but again, soon to be. Now, you might not want to rewrite all your parameterization because some of them might be good, right? I mean, some of them might be pretty good, but you just want to tune the parameter, or relearn the parameter. And so that's something we can do as well. I don't need to come up with a brand new one. We can take one, say, vertical mixing that, is a pretty good one, the one that exists in this climate model. And the parameter itself is actually a little uncertain. It's basically has one piece that is very physically grounded, but has a vertical profile and a velocity that is kind of an old approximation that is a little bit ad hoc. So one thing one can do is, again, use simulation, high fidelity simulation, to learn with a neural network the vertical profile that, again, was ad hoc previously across a wide range of forcing, and this kind of velocity scale with a simple network, and replace them in the model. So now those are very simple functional form. So again, we can implement them in the simulation very cheaply, very easily, and show that some of the errors, in this case in the tropics, are actually improved compared to the original parameterization that has those ad hoc parameters. So again, you don't need to completely, scratch your parameterization. Some of them are quite good. It's just that a few approximations are wrong. So again, they can be implemented. So all of that is to show you we are now, able to do those things, right? We can really go and test if we are improving climate simulation, online. So let me give you a few thoughts in the last few minutes. I think there are a lot of advances, right? Like in computer science, there's no doubt about it. I think, again, at MIT, there is a new ocean model that is faster than ever. But again, if we want to run fully coupled simulations, we still have a long way away, right? So being able to actually leverage some of the techniques that we have now to both improve physics and simulation is going to be important. And that means parameterization are going to be with us for a very, very long time until we can actually resolve all scales of motion, which, again, if we want to do 100-year simulations and ensemble, it's not going to happen. I don't think it's going to happen in my lifetime. So parameterization are still here with us. Can we really use those data-driven machine learning in a principal way, right? Still not just trying to learn things that are black box, but something that really capture the essence of the physics that we were missing to improve climate models. So again, those kind of, robust, interpretable, and flexible continue to be guiding principle the same way we do, basic physics or engineering problem overall. And so I think there are some advances there, but we still have some challenges, right? So I don't know, I was always told a challenge means an opportunity. So let's take them as opportunities, right? So one is, how do you use data? So the type of data, we learn from data. So you better have good data. That's kind of the bottom line. I showed you things with high fidelity simulation, but they're still simulations, so they have errors. We have observations, but often we don't have enough of them to learn those kind of missing physics. And they are uncertain. They usually don't directly measure the quantity that you want. They measure something and then you infer it and so on and so forth. So there's a lot of ways to think about, using the data. Again, UQ will be important. But I think there's a lot of opportunities there to kind of try to think about this. One thing we've been doing is kind of the cheap way, is we've been using data indirectly. So I showed you a high fidelity simulation, but there are other type of data sets out there. One of them is data assimilation products. So data assimilation is a combination of a simulation, of a forward simulation and observations. And usually you take, and I'm going to explain it in a very crude way, but you have observations with some error bars with it. You have your simulation, and you try to do a weighted average of them in a way to try to emulate, the observation as a function of time in a way that is a combination of your model and your observations. When the observations are really good, you're going to weight more towards the observations. When they're not, then the model might actually take over. So those kind of corrections, or those averages, when you take the model and try to correct it with observations, it's been shown that if your model is actually biased in a certain way, over a short amount of time, every time you correct, the model will actually, the correction might actually project on the long-term bias of the model. Meaning you can learn a lot by looking at short-term correction with observations compared to the long-term model bias after you run it for 30 years. And that's been shown in the atmosphere, in the ocean, and in the sea ice models. That means there is information in this kind of data assimilation increment over 5 days. That means you don't need to run the model for 60 years until you see the model being wrong compared to the obs. And so there's kind of something nice here, is that we can use those short-term corrections as something to learn in terms of the missing parametrization. And so now we've actually used observations, again, indirectly, to learn the missing physics. And so here are some examples for the ocean and sea ice, where we can really improve the long-term model bias by learning from very short-term correction. So again, there's something appealing here where we can indirectly kind of learn from observation. But it's non-trivial, it doesn't always work, and you might actually just learn, kind of numerical error more than you learn physics. So there's still a lot of things to think about. Which physics did we learn, and did we improve anything? As I said, that was one example before. With neural network, it's also hard to tell. And if you didn't learn any physics and you didn't improve your model, maybe we should just not bother and just emulate stuff all the way. I don't need to learn a parametrization. Maybe I can take a high fidelity simulation and build a full emulator of the time evolving climate system and just hope for the best, right? I mean, you can see me shrugging, so I don't really believe that's gonna be the way to go. I don't think we have enough high fidelity simulation to actually really capture the full complexity of the climate system and trust it if we want to make climate projections. I don't think that's possible. But there are a lot of things where those ideas can come about. Short-term weather forecast, I think it can. But I think generating cheap simulation is also great. And we can do it by actually generating cheap simulation of those high resolution ones and maybe use them to calibrate our parametrizations or do data assimilation with it. So it's kind of, again, another way to kind of combine, different methods together. And so something to think about. So I talked about numerical stability, tuning, calibration, UQ. I think, again, this kind of idea of interfacing between scientific computing and scientific machine learning, I really think it's the future. I think this is really where we're going. I think it's not one or the other. We replace everything with ML, or we stay with the old way to do scientific computing. I can't see it any other way if we want to make really step changes in the way we actually simulate problems, fluids, climate, but many other topics in science. And so I really think this is where the future lies. And so I'll just leave you with a little simulation. One way we've been trying to actually bring people in, because we train people that come from scientific computing or climate or ML, is to try to actually build kind of an infrastructure, a data infrastructure where we have a Jupyter hub, we have all of our data sets, and everybody can interact on those data sets, either train the machine learning, so it's a Jupyter hub on the cloud. People can train the machine learning model. They can actually play with the simulations that we have, kind of do some visualization if they wanted. And it's really kind of a nice way to kind of bring people in and be able to either play with machine learning or play with the climate simulations or learn something about the physics in a way that does not requires you to know everything about everything in a problem that is, again, quite challenging. So if you want to learn more, we've got all our publication code, everything is online and open, and happy to take questions if there are any. Thank you.
Thank you for the talk. So we have like 5 minutes for questions. I don't know if people online, but we will start with the people here. So any questions? Yes.
So the data optimization, the example for us, so you mentioned I've done practice long learning prediction, doing short applications. Which kind of
Yeah, so each one of them is a little bit different. So because we use existing operational system, so some use ensemble Kalman filters. I mean, most of them actually use ensemble Kalman filter for the main part. So we only use the product as is. We don't go and change the data simulation product ourselves. Yeah.
Right. So for the machine learning models to conserve mass and momentum, do you add it as a penalty term to your loss function, or do you, or have you also thought of ways to maybe change the architecture itself that can enforce these constraints?
Yeah, we do both. I mean, different models have been built differently. So in some of the ocean turbulence, the way we do it is in the last layer of the architecture itself, when it's a full CNN, we learn terms in the tensor and then takes the divergence. And again, because of conservation, when you integrate over the domain, it has to give you 0. So that's baked in the architecture. We have to learn a symmetric stress tensor that will be conservative. Sometimes it's harder to bake in when you have open boundaries and so on and so forth. So we have a penalty in the loss function. The disadvantage, of course, of the loss function is it's only an approximation, right? You tend towards conservation. It's not a strict guarantee. So it's always the pros and cons. But yes, we do both. Yeah.
This machine learning model, is it tied to the horizontal distribution? So when you want to change the distribution, that's really cool.
Yeah, it's a great question. So initially, we learn for one given resolution in a way that we coarse grain to a given scale. And so with the CNN, you end up being tied a little bit to a resolution because you learn on the grid. So now we've been actually kind of generating those data sets where we learn across resolution. So then we don't need to do that anymore. Yeah. It doesn't always work. Again, I should make clear. None of what I talked about works 100% of the time.
One question. You mentioned very briefly about discovering the equation, like an analytical form, kind of mixed hybrid version. You made some comments about what is the approach we follow to do that?
Yeah, so we have, so we follow two approaches. The first one, when we did equation discovery, first one is kind of a dictionary-based approach, meaning we still want to learn an equation that will best represent the data. You're going to use a set of basis functions that you believe are useful. So again, for ocean turbulence, it's going to be shear, stress, and all this kind of stuff that we know are useful. And we're going to write a set of basis function, a set of functions that are related to those quantities. So it can be vorticity share, vorticity squared, and so on and so forth. And we're going to ask the algorithm to go and prune that library of function that best matches the data, but also penalizes it. So there has to be as few terms as possible. So that's one approach. So you select from a library of function. It's a fancy, linear regression if you want, right? You're just linear regression with a penalty that I don't want to have a million terms. I want to have as few as possible. So that's one. But now the problem is, if you want to learn something you really don't know at all, or you don't want to build a full library of function because it's going to be memory intensive and computationally intensive, genetic programming can actually build trees by actually kind of, adding, multiplying, dividing different input features, and we'll come up with kind of the same set of equations, but without predefining what it is. Problem with that, it knows no physics. So it might add two quantities that have completely different units, which is not good. So we combine it with sparse regression to make it more physically based. So yeah.
In the other extreme, when you use a CNN, how do you make that compatible later with a complex geometry? And CNN is taking spatial structure. Now you have complex geometry, you cannot fit that.
Yeah. So yeah, correct. So padding, right? So we're going to use the land mask to actually kind of, use that. And the second thing is in the simulation, we have boundary conditions, right? So if we learn an acceleration, we know the acceleration cannot penetrate through the wall. So then we're going to basically use those kind of concepts through it. Yeah.
More question? Thanks a lot for the
Thank you.
great talk.
Thank you. Sounds great. Oh, yeah, absolutely.